Hello and welcome to another lecture with Dr. Armand. Today we'll be talking about periodic trends. Such periodic trends are valence electrons, atomic radii, ionic radii, ionization energy, electron affinity, and isoelectronic species. So sit back, relax, and enjoy the chemistry show. Okay, so as I said before, today we'll be talking about periodic trends. So before we do that, we want to get a little bit, maybe some refresher questions on things we've talked about before. And also periodic trends. So one periodic trend is the number of valence electrons. And so for main group elements, and again, main group elements are group 1, group 2, group 13 through 18. Number of valence electrons increase from left to right. So as you go from left to right on the periodic table, when you're talking about main group elements, the number of valence electrons increases. And so the group number identifies the number of valence electrons. So we start with group 1 has 1, group 2, 2 valence electrons, group 13 or 3A, 3 valence electrons, group 14, 4A, 4 valence electrons, group 15 or 5A, 5 valence electrons, group 16 or 6A, 6 valence electrons, group 17 or 7A, 7 valence electrons, and then the noble gases have 8 valence electrons. So main group elements, the maximum they can have is 8. And again, the group number tells you the number of valence electrons. It increases from left to right, and we'll explain why it increases. Because you get more electrons in the outer energy orbital. So here we want to know how many valence electrons does thallium have. So thallium is located right here in group 3A, so it has 3 valence electrons. Three. Look at another problem. Here we want to know, we have this orbital diagram of an ion with a +4 charge. And we want to identify what the ion is. So we have some ion with a +4 charge. What's the identity of the element that would have this +4 charge? And we're given that the ions, so some element X with a +4 charge has this electron configuration. So remember, for transition metals, cations, you remove from the S, then D orbital. Highest S and D orbital. And so if we want to find out what the identity of this element is, we're going to do the opposite. We're going to add electrons back to the highest S and then the D orbital. So let's draw another orbital box here, and this is the 4 s. And so we need to add back 4 electrons. So let's first add 2 to the 4s, so we get 4s2, and then we have 2 left to add, so we add 1 here and here. So which element is a D4 element on the third row? So we go 1, 2, 3, 4. Chromium is a D4 element. So this species is chromium plus 4. So that's the element that would have this ion, chromium. So the first type of periodic trend is we're going to talk about atomic radius. So again, atomic radius is actually an average of bonding radii from measurements on a large number of elements or compounds. So it's an average. And what we see is as we go from left to right, atomic radius decreases. Remember, as we go left to right, valence electrons increases. We talked about that in previous slides. So atomic radius decreases as we go to left to right, and we'll explain that in just a moment. And it increases down a group. So the elements like helium, neon, fluorine, some of the smallest elements. And then on the opposite end, cesium, francium, radium, some of the largest elements. So again, as we go left to right, atomic radius decreases, and as we go from top to bottom, atomic radius increases. And we'll talk about why in just a moment. And so to explain the, I guess, of trends in atomic radii, we need to discuss 2 terms here that help explain this. So first off, one is called the effective nuclear charge. And so the effective nuclear charge is the charge felt by the electron from the nucleus. And so as you can imagine, the farther away the electron is from the nucleus, the less it will feel that charge. And so a higher effective nuclear charge interacts stronger than something with a lower effective nuclear charge. And so again, the charge felt by the electron from the nucleus. So the farther away the electron is, it feels less pull from the nucleus. And also the more electrons in that same energy level also interacts or affects the effective nuclear charge. And when you have electrons competing for this charge, you get something that's called shielding. And shielding is based on electron repulsion of sublevel energies. So what happens is, for example, if we look at this diagram over here of, what is it? 10 electrons, I think that's neon. So this electron here in the outer orbital feels less of a pull to the nucleus because it has electron repulsion between the electrons in the same orbital. So these are repelling one another. And also electrons in inner orbitals. So the closer you are to the nucleus, the stronger the pull is because there's less electron-electron repulsion. So outer electrons feel less of a pull. If there's more inner electrons, there's more shielding occurring. So shielding pushes the outer electrons further out. And we can actually calculate the effective nuclear charge of an electron. And one thing to remember is the lower the effective nuclear charge of an electron, the easier it is to remove. And this equation here gives you an approximation. So you take the number of protons minus the number of inner electrons, and that'll tell you the effective nuclear charge of it. So here, if we take this example of neon, so we want to calculate the effective nuclear charge of the outer electrons in neon. So it's 10 minus, and there are 2 inner electrons. So this has an effective nuclear charge of +8. So it's very tightly bound to the nucleus. So remember, neon is helium 2s2 2p 2s2 2p6. So it feels an effective nuclear charge of +8. So shielding and effective nuclear charge are opposite of one another. So as you go left to right on a periodic table, effective nuclear charge increases. As you move from left to right on periodic table, shielding decreases. So these are opposite of one another. If you have a high effective nuclear charge, you're going to have less shielding. And you know, the main focus of shielding are the inner electrons, but even sometimes the other electrons in the same energy level cause shielding as well. So these are things to remember. They're going to help us explain why atomic radius decreases from left to right. So let's look at effective nuclear charge. So again, when you have outer electrons, it does feel a pull from the nucleus. However, it's going to have repulsion from the inner electrons, which is going to push it out. So for example, here we have hydrogen, which is a +1 charge. It's going to attract this electron, but it's only +1, so it's not a strong attraction. But if we increase it to a +2 charge in the nucleus, you see there's a greater attraction between the nucleus and that electron. And this is noticed by the change in energy that is required when it is removed. And then if we go to a +3 charge, we see a very strong attraction between that electron and the nucleus. You know, almost a 10-fold difference in the amount of energy needed to remove that electron. So what is trying to be illustrated here is that the greater the effective nuclear charge, the stronger those electrons are held to the nucleus. So if you have a high effective nuclear charge, it's going to hold those electrons tightly. And that's why the inner electrons are very hard to remove, because they have a very strong pull with the nucleus. Now we get to shielding. And as I said before, shielding is when the result of electron-electron repulsion between electrons in the same energy level and also in the inner energy level. So for example, if we look at the same energy level, here at the bottom, we just have one electron. And it takes about 5,000 kilojoules of energy to remove this electron from this pool of the nucleus. However, if we introduce another electron on the same energy level, now there's electron-electron repulsion between those two electrons. It becomes easier to remove those electrons, and this is denoted by the less energy needed to remove an electron. Now, if we, instead of adding electrons in the same energy level, if we put the electron further out, so instead of saying a 1s electron, now it's a 2s electron, and we have 1s electrons in front of it. So now this 2s electron has electron-electron repulsion between the inner electrons and the inner electrons. There's no more outer electrons, there's only one outer electron. And so this outer electron becomes easy to remove because there's a lot of repulsion between it and the inner electrons. And that means there's less attraction between that outer electron and the nucleus. So that's why it's a very low amount of energy needed to remove it. And so if we look at potassium here on the right-hand side, as you go to higher energy levels, the electrons feel less and less effective nuclear charge. And that's why it's easier to remove an electron from an outer energy level, because it has less of the effective nuclear charge. Now, why does atomic radius decrease from left to right on the periodic table? So again, why does atomic radius decrease from left to right on the periodic table? Is because as you go from left to right, A, valence electrons increase, which are your outer electrons, and B, effective nuclear charge increases, so there's greater attraction. C, shielding decreases. So all these three factors cause the electrons to become more attracted to the nucleus, causing the nucleus to shrink. So now we look at the periodic table and the shielding effect. So we see lithium, sodium, potassium. The radiuses get bigger for these elements. So now if we look at lithium, let me go back. So for lithium, sodium, potassium, as we go down a group, atomic radius increases. We go down a group, and so can anybody tell me why you think the atomic radius increases down a group by looking at these three elements? And the reason it increases down a group is because as you go down a group, what's increasing? The number of inner electrons. Since you have more inner electrons, you need more energy levels to put those electrons in. Since you need more energy levels, the radius gets bigger. That's why as you go down a group, the number of electrons increase, so therefore by default, you need more energy levels to put the electrons in. Just like if we had a classroom, as the number of students increases, you got to add more desks to the classroom to accommodate the increase in students. So you need a bigger classroom. Same concept here. So now if we look at this, we have lithium. This is a Bohr's model interpretation of lithium. So it has that one outer electron here, and it's being shielded by the two inner electrons on the 1s orbital. And since it's being shielded by those inner electrons, it feels less of a charge from the nucleus. So the effective nuclear charge for that outer electron is +1. So it doesn't feel the full +3 charge from the nucleus. And just for reference, its radius is about 152 picometers. Now if we go from left to right, we look at beryllium, which is next to lithium. And what we notice, the difference between beryllium and lithium is now that we have an extra outer electron. So now not just one outer electron, we have two outer electrons. The number of inner electrons remains the same, and the nucleus's charge increases. So since there's two outer electrons and the number of inner electrons has remained the same, those two outer electrons are more attracted to the nucleus because their effective charge is more. For lithium, it was +1. For beryllium, it's +2. So greater attraction of those outer electrons to the nucleus results in a smaller radius. And so notice lithium was 152, beryllium is 112. Now we go to oxygen, and oxygen still has two inner electrons. So we still have two inner electrons for oxygen, but now we have 6 outer electrons. So it's like having a pop star with only 2 bodyguards, and you have like 8 people trying to, or 6 people trying to get to the pop star. Well, the fewer bodyguards you have, the easier it is for those fans to get to the pop star. And so since we have 6 outer electrons and 2 inner electrons, the effective nuclear charge increases. Now those outer electrons feel a +6 charge from the nucleus. So again, greater effective nuclear charge shrinks the radius because those electrons are more tightly held to the nucleus. And so oxygen has a radius of about 73 picometers because again, more valence electrons, less shielding, greater effective nuclear charge, smaller atomic radius. Now let's look at sodium. So sodium has 11 electrons, 1 in the outer energy level. So if the outermost electron feels a +1 effective nuclear charge, and what happens as we go down a group, we have more electrons, we need more energy levels. Higher energy levels have larger orbitals, therefore the radius increases. Well, as we compare it to lithium, which only has 3 electrons, they still have an effective nuclear charge of +1, but since sodium has more electrons, it needs more energy levels, so therefore it has a larger radius. So let's look here. We have some species. We want to know which one has the larger radius. So as we talked about, as you go from left to right, atomic radius decreases. As you go from top to bottom, atomic radius increases. So the elements on this side of the periodic table are larger. So we'll put an L for larger than the ones on this side, which are smaller. So you have the range between them. So we want to look for the elements that are on the left-hand side of the table. So is francium on the left-hand side of the table? Yes. So we can look at that one. Arsenic? No. Tin? No. Aluminum? No. Chlorine? No. These are all nonmetals and metalloids. Iodine? No. So the only metal we have is francium. So francium has the largest atomic radius because it's the furthest one on the left side. Left and down is where you want to look. So francium is right here. It's actually the largest element in the periodic table so far. Now we have these. We want to know which one has the smallest atomic radii or radius. So again, smallest atomic radius, we're going to be looking in this corner. So we're going to be looking at nonmetals. So let's see which ones are nonmetals. Calcium is a nonmetal? No. Palladium? No. Selenium, yes. Chlorine, yes. Iodine, yes. Aluminum, no. Potassium, no. So we've narrowed it down to selenium, chlorine, and iodine. So here's selenium, chlorine, and iodine. So which is the one closest to the top right? That is chlorine. So that would be the one with the smallest atomic radius. So now we get to ionic radius. So here we have sodium, and what you don't realize with sodium is that the outer electron causes a lot of disturbance, which results in the radius being very large. Now if we go to sodium plus, you see we remove that outer electron. Since you remove that outer electron, there's less electron-electron repulsion, so the radius shrinks. So when we're comparing the cation to the neutral element, the cation is smaller. So again, cation smaller than corresponding neutral element. So sodium plus is smaller than sodium. And again, the greater the positive charge, the smaller the radius. So for example, if we were comparing iron, which is larger than iron 2 plus, which is larger than iron 3 plus. Because as the more electrons you remove, it generally leads to smaller atomic radius. Now for anions, here we look at oxygen. We talked about how, as you get more valence electrons, greater effective nuclear charge, less electron-electron repulsion. But when we go from oxygen to oxide, we're actually starting to crowd the energy level, the outer energy level. So what happens is there's more electron-electron repulsion, causes the radius to increase. And so the greater negative charge of the ion, the larger the radius of the ion. So anions radii are much larger than their corresponding neutral elements. Anions corresponding. So for cations, they're smaller than their neutral counterparts because there's less repulsion. For anions, they're larger than their neutral counterparts because there's more electron-electron repulsion, pushing the electrons further out. So this is just an overview. So you see magnesium 2 plus is going to be smaller than magnesium. Sodium plus is smaller than sodium. Generally, the larger the charge, the smaller the radius, etc. The greater the negative charge, the larger the anionic radius. That was atomic and ionic radii. Now we're going to be talking about ionization energy. So ionization energy, and this is very important, is the energy required to remove an electron from an atom or an ion in the gaseous state. So you have to be in the gaseous state. You apply a certain amount of energy, so it's an endothermic process, and then you remove the electron. So if you remove the first electron, it's called the first ionization energy. And as many electrons as you have that many ionization energies. So we remove the first electron, it's called first ionization energy. For sodium, it's 496. So if you apply 496 kilojoules of energy, you can remove the outermost electron in sodium. And then if you were to take that product from the first ionization energy, apply more energy, you would remove the second electron, which would be the second ionization energy. And notice that when we go from first to second ionization energy of sodium, we have almost a tenfold increase in the energy. So what's happened when we from going from the first to second electron in sodium, from the outermost electron to the secondmost outer, from the outer electron to the secondmost outer electron? What's happened? And so what's happened? That's correct. We've dipped into the inner electrons. So when you go from outer electrons to inner electrons, you're going to see a big increase in the ionization energy. So wherever you see that jump where it goes from small to big, that tells you that you've gone from outer to inner electrons. And so the more electrons you remove, the more energy it takes. And so if there's enough, however many electrons is how many ionization energies you can have. Now we're only going to be focused on the first ionization energy trends. And so the trends go like this. As you can imagine, as you go from left to right, ionization energy increases. It takes more energy. And why is that? It's because you have increased effective nuclear charge. Atoms are held more closely to the nucleus, so it takes more energy to break them. And it decreases down a group. And the reason is because those outer electrons are further away. It takes less energy to break them. So again, why does it increase from left to right? Because you have greater effective nuclear charge, electrons are held more tightly, so it takes more energy to remove the electron. Why does it decrease down a group? Because you have more electrons, the outer electrons push further out, causing it to take less energy to remove it. And we are going to look at some exceptions as well. But on the bottom table, it's important to note that the ionization energies in white are from outer electrons. The ionization energies in orange are inner electrons. And what you notice is as you go from outer to inner electrons, you see a big increase in energy. That tells you when you're jumping from outer to inners, when you see that big jump in ionization energy. And so there are two exceptions you need to know, and again, need to know, repeat, need to know, which are important. The first one is group 2A and group 3A. So generally as you go left to right, ionization energy should increase, but in one exception is group 3A has lower ionization energy than group 2A. And the reason is because it's easier to remove an electron from a higher energy orbital than it is from an orbital of the same energy with paired electrons. So this 2s here is very satisfied. It doesn't want to give up its electrons. But here this 2p has one lone electron. It causes a lot of, it's high energy orbital, one electron, very, it doesn't take much to remove that electron from it. So group 3A have lower ionization energy than group 2A, and this is true to about the fourth row. After the fourth row, the exception goes away. And if you'd like to learn why, you can continue in chemistry, and they may talk about it in inorganic chemistry. So again, that was group 2A and group 3A. That's one exception you need to know. Yes? Thank you. The next exception is group 5A and 6A. So here we don't have electrons in different orbitals. We have the same number of electrons. We have the same types of orbitals, just different number of electrons. And so what we notice here for nitrogen, there's one electron in each 2p orbital. But in oxygen, we have one pair of electrons in a 2p orbital and then two lone electrons. So what happens is it's easier to remove an electron from a pair of electrons rather than by itself. So therefore, oxygen has lower ionization energy than nitrogen. And this is true for the first four rows. Group 6A is lower in ionization energy than group 5A because it's easier to remove this pair of electrons versus an electron by itself. So here's just an overview. So as you can see in row 2, group 3, boron is less than beryllium, aluminum is less than manganese, gallium is less than calcium, but after the 4th row it disappears. Indium is greater than strontium. And group 5 and 6, oxygen is less than nitrogen, sulfur is less than phosphorus, but you see the intensity decreases as you go down the rows. Selenium is less than arsenic, but you notice tellurium is greater than antimony. Also, what I want to show you is that, again, when you make that big jump, you're going from inner to outer electrons. For example, beryllium, the first 2 ionization energies are relatively the same, but when you jump to the 3rd ionization energy, it's a very large increase, almost 10-fold increase, due to the going from outer to core or inner electrons. So we'll look here, which of the following would have the lowest ionization energy? So again, it increases left to right and decreases down a group. So we want to look at metals. So metals on this side would have very low ionization energies. So is neon a metal? Why no. Oxygen? Of course not. Now we're left with titanium, cesium, lithium, aluminum. So aluminum is over here. Titanium is a transition metal, lithium, and cesium. So cesium is in this area that have very low ionization energy. So cesium would have the lowest ionization energy. Which of the following are incorrect in regards to the first ionization energy? So let's look at these. Does aluminum have a greater ionization energy than magnesium? Is that correct? Yes or no? That's correct. No, aluminum is actually less than magnesium, because remember, group 3A is less than group 2A. So this one is incorrect. It should be flipped. Is silicon greater than aluminum? Well, aluminum is here, silicon is here. As you go this way, it increases, so that one is okay. Is chlorine greater than sulfur? So again, chlorine is further to the right than sulfur. That's correct. But is sulfur greater than phosphorus? That is incorrect, because remember, group 6 is less than group 5. So we drew it like this. So that's an incorrect comparison. And is magnesium greater than sodium? That is correct. So the choices are A and D. You got to remember the exceptions. Group 3A less than group 2, and group 5A is greater than group 6. So sometimes it may ask you to calculate the wavelength needed to ionize a magnesium atom. So here you need to know the trends in ionization energy, and then you can determine what's the ionization energy for magnesium. So for magnesium, you need an ionization energy of 738 kilojoules per mole. That's the first ionization energy. What we're going to do is, to find the wavelength, we're going to convert this to joules. 7.38 e to the 5th joule per mole. In order to use the equation lambda equals hc over energy, we got to convert energy to joule per photon first. So what do? We take the energy divided by Avogadro's number. So joule per mole times 1 mole divided by 6.022 e to the 23rd photons. This will get us the energy of 1 photon. This would be 1.23 e to the negative 18 joule per photons. Now that we have joules, we can find lambda. So lambda equals 6.626 e to the negative 34 times 2.998 e to the 8th divided by 1.23 e to the negative 18. And this will give us the lambda in meters. We get 1.62 e to the negative 7 meters. Now we got to convert this to nanometers. So 1.62 e to the negative 7 meters times 1 e to the 9th nanometers divided by 1 meter. This will be 162 nanometers. And this would be a UV photon. So that's how you solve for the wavelength of a photon needed to ionize a magnesium atom. Got to use what you learned in previous chapter. Another type of problem is it could give you a list of ionization energies and say, hey, what third row element would fit these ionization energies? So what we're looking for is a big jump. So let's look at these ionization energies. So we have first ionization energy, second, not a big jump. Third, still not a big jump. Fourth, from 3 to 4, not a big jump. So you see from 1 to 2, 2 to 3, 3 to 4, not big jumps. But when you go from 4 to 5, what do you see? You see a big jump, almost 10,000, over 10,000 increase in the energy. So what that means is this is the boundary between outer and inner electrons. So let's count the number of outer electrons we have. We have 1, 2, 3, 4. So what third row element has 4 outer electrons? So 1, 2, 3, 4. So the answer is silicon. So whenever it gives you a list of ionization energies, you see where the big jump is. Before that is your outer electrons. After that is inner electrons. Another periodic trend we're going to be discussing is electron affinity. And so electron affinity is the energy released when you add an electron to an element in its gaseous state. So these are exothermic, we're releasing energy. So it becomes more favorable when you add an electron. And as you can imagine, electron affinity increases from left to right because it's more favorable to add an electron to a non-metal versus a metal. And it increases as we go up a periodic table. Now notice here that 2A and 8A have asterisks. That's because group 2 and 18 have completely filled orbitals and cannot accommodate any more electrons. So they have to add it to a higher energy orbital, which is unstable. So these have no electron affinity. So groups 2 and 18 have no electron affinity because their orbitals are already filled and you can't add any more electrons to those orbitals. So they do not have electron affinity. Now with electron affinity, there are exceptions. So the first one is obvious, group 1A and 2A. So group 1A and 2A, here this should be, this should be 2P versus 2S. This should be a 2. So 2P, 2S. And so it's easier to add an electron into a 2s orbital versus a 2p because 2s is the same energy as the electron that's already in there. So again, it's easier to add an electron to a 2s orbital rather than an electron in a 2p, which is a higher energy orbital. It's unstable. And this is the case all the way down the periodic table. Group 1 has greater electron affinity than group 2 corresponding group 2 elements on the same periods. Next we have group 4A and group 5A. So you'll notice here the only difference between group 4 and 5 is that group 5 there's one lone electron in each 2p orbital, and group 4 one of the orbitals is empty. And so it's easier to add an electron to an empty orbital versus an electron that already contains one electron. Just like when you're on the bus, it's easier to sit in a seat that's empty versus a seat that has some stranger in it. So the same thing is true. Carbon has an empty orbital. It's easier to put an electron in it, so it has a greater electron affinity than nitrogen. And this is true for all corresponding pairs on every row. 4A is always higher in electron affinity than 5A. Now let's look at some examples. So again, these exceptions are important for you to know. So here we want to know which of the following elements has the greatest electron affinity. So again, it increases as we go up a group and increases from left to right. And what we know is that group 2 and group 18 have no electron affinity. So if we see any of those, we can cross them out. So xenon is group 18, strontium is group 2. Then we can look. So the ones with the greatest electron affinity will be in this area. So metals we can mark off. So rubidium is a metal. It's all the way over here. It's going to have very low electron affinity. Tin is right here. Then we have antimony and indium. So these three are in a row. So we have to look and see which one is furthest to the right, and that's going to be antimony. So antimony you would think is the one with the higher electron affinity, but what did we just talk about? That's right, we talked about exceptions. So we had these marked. And so remember, group 4A has higher electron affinity than group 5A. I almost caught myself in that trap. So while you want to say antimony is greater than 10, actually 10 has the highest electron affinity because there's that exception. So 10 is the correct answer. One last periodic trend is properties of monoatomic ions, and these are ions that have a noble gas configuration. And what's unique about these ions is that they're isoelectronic species. It means they have the same electron configuration, the same number of electrons. The only difference is the charge of the species. So what you see here is each row has its own isoelectronic species. So for example, hydride, helium, lithium, and beryllium 2+, they're isoelectronic. Nitride, oxide, fluoride, neon, sodium, magnesium, aluminum is 3+ are isoelectronic. And so for isoelectronic species, the greater the negative charge, the larger the radius. The greater the positive charge, the smaller the radius. And this is only for isoelectronic species, so species with the same number of electrons. And there are like 1, 2, 3, 4, 5 common isoelectronic series shown here. So the greater the positive charge, the smaller the radius. The greater the negative charge, the larger the radius. I spelled isoelectronic wrong. It should be R before O. I'll fix it because I don't want anybody to say anything. Isoelectronic. There we go. Let's look at some examples involving this. So we know which species would have the largest radius. So remember that from what we learned, radius increases as we go down a group as we go this way. So we have scandium 3+, scandium is right here. We have chloride, chloride is right here. We have potassium plus, calcium 2+, sulfide, phosphide, and argon. So all of these species, what do they have in common? They have the same number of electrons. So which one of these has the greatest negative charge? It's F. And so phosphide would be the one with the largest radius, because again, they're all isoelectronic. They have the same number of electrons, 18. Here we want to know which one has the smallest radius. So again, what do we have? We have calcium 2+, potassium, selenium, and selenide, bromide, arsenide, and krypton. So these aren't isoelectronic, but what you notice is that potassium K+ and calcium 2+ have 18 electrons, whereas arsenide, selenide, bromide, and krypton have 36. So between potassium and calcium, these are isoelectronics. So which one would have the smallest radius? It would be calcium because it has a greater positive charge. Because again, calcium 2 plus and potassium are isoelectronic. So that concludes today's lecture on periodic trends. Again, there was valence electrons, atomic radii, ionic radii, ionization energy with those exceptions, electron affinity with exceptions, and then isoelectronic species. So that concludes, the chapter on electron configuration periodic trends. The next time that we'll be presenting a lecture, it'll be over Lewis structures. So on that note, goodbye and until next time. Signing off. Well, I was signing off. Let me sign off.